In this video, I will talk about the Pauli exclusion principle, which is one of the cornerstones of quantum mechanics and the reason of our existence. I will show how we can prove it mathematically by using a very simple model. The physical world can be divided into classical particles and quantum particles. Let's have a look at classical particles first. These particles are distinguishable. If we have a system of two classical particles and exchange them, for example by reassigning energies, then the probabilities of finding them somewhere would change too. We can express this in terms of probability densities. So psi of x1, x2 modulo squared is different to psi of x2, x1 modulo squared. In contrast, quantum particles can be identical, which means they are indistinguishable. It turns out that in this case the probability densities won't change under particle exchange, and we can express this with the equation psi of x1, x2 modulo squared equals psi of x2, x1 modulo squared. This therefore requires that the wave function under particle exchange is either equal to the original wave function or it's negative. Now, let's have a deeper look into how the probability densities change under particle exchange of two distinguishable particles in an infinite square well. A system of two distinguishable particles can be described by a product wave function, that is, by a product of the two individual wave functions. So we can write psi a of x1 times psi b of x2. Here, a denotes the ground state energy and b the first excited state. The wave function of the excited particle has two extrema. The wave function of the ground state particle has one extrema. This leads to two peaks of probability densities depicted here as contour plots. If we exchange the particles, the total wave function is psi a of x2 times psi b of x1. Particle 2 is now in the ground state and particle 1 in the first excited state, represented by the appropriate wave functions. When we draw the contour plots of the probability densities, we again see two peaks, but they are spatially aligned differently than in the original situation. The root cause is that the wave functions are not the same anymore and neither symmetric nor antisymmetric to each other. Let's see how the probability densities change under particle exchange of two indistinguishable particles in an infinite square well. A system of two indistinguishable particles can be described by a wave function of two particles in an entangled superposition. If A and B are the ground and first excited states, respectively, the total wave function can be constructed as 1 over square root 2 psi a of x1 psi b of x2 plus psi b of x1 psi a of x2. When we do the particle exchange, we see that the first term of the first equation equals the second term of the second equation, and the second term of the first equation equals the first term of the second equation. That is, we show that the total wave function does not change under particle exchange. But there's another possibility, namely if the wave function after particle exchange is the negative of the original wave function. This time, the total wave function is 1 over square root 2 psi a of x1 psi b of x2 minus psi b of x1 psi a of x2. When we do the particle exchange in this case, we see that the second term of the second equation is the negative of the first term of the first equation, and the first term of the second equation is the negative of the second term of the first equation. Here, the total wave function under particle exchange becomes the negative of the original wave function. But since the probability density is defined by the overlap, that is the inner product or simply the modulo squared of the wave function, it remains the same. The first wave function is symmetric under particle exchange and applies to bosons. The second wave function is antisymmetric under particle exchange and applies to fermions. Here is a visualization of the probability densities of two indistinguishable particles in an infinite square well, one being in the ground state and the other in the first excited state. If particles have a symmetric total wave functions, we have two peaks and we see that the probability densities don't change under particle exchange. Indeed, the particles tend to be at the same location. If particles have an antisymmetric total wave function, we have two peaks again, and we see that the probability densities under particle exchange don't change either. However, contrary to the bosons in the first case, the fermions here tend to be at different locations. We now come to the core argument of this video. The Pauli exclusion principle applies to fermions. That means to particles with antisymmetric total wave function. We write it down once again. Psi f equals 1 over square root 2 psi a of x1 psi b of x2 minus psi b of x1 psi a of x2. Now, let b equals a, that is, let both particles be in the same state, then psi of psi f equals 1 over square root 2 psi a of x1 psi a of x2 minus psi a of x1 psi a of x2. And this is 0. The wave function vanishes, which proves that for fermions, no two particles can be in the same state. And that's it. The famous Pauli exclusion principle proved by math. So far the theory. Let's investigate a real-world example. Lithium has 3 protons and 3 neutrons. A neutral lithium atom therefore accommodates 3 electrons. Electrons are fermions and need to obey the Pauli exclusion principle. However, 2 of them are in the lowest energy state, as you may notice. This is possible since electrons not only can take different energy states, but also 2 different spin states, up or down. But that's it then for the lowest energy level. And this is why the third electron is forced to be in the first excited state, essential for lithium's chemical and metallic behavior. The consequences of the Pauli exclusion principle are immense. Here are 3 striking examples. First, it is responsible for atomic structures and atomic properties. Only with it can chemical reactions, biological processes, and ultimately life take place. Second, it is responsible for degeneracy pressure, which means that fermions such as electrons and neutrons are forced into ever higher energies, preventing white dwarfs and neutron stars from collapsing. It is, third, responsible for the band structures in solids, which leads to conductors, insulators, and semiconductors. Some closing remarks. The key assumption of the Pauli exclusion principle is that identical particles like fermions must have an antisymmetric total wave function. Further questions arise though. Why? This exploration goes beyond this video and my current personal knowledge and remains an exercise and motivation for the viewer. Feel free to discuss in the comments. Here are 2 keywords that could serve as a starting point: special relativity theory and violation of causality. Thank you for watching and see you next time.